Hello everyone and welcome back to another pattern recognition lecture video on deep learning. In this video we'll look at how deep learning architectures can be constructed to deal with sequential data. So far we're mainly focused on image analysis, but a lot of data is in fact sequentially structured so that the order of the data entries matters. This could for instance be the case in language analysis, time series, biological data and so on. I would say that this video here will only give you a very top level overview of the topic of sequence modeling. But as usual, there's a lot of references to where you could go and get a lot more insight to this, this whole area of sequence modeling, recurrent neural networks and so on. From the content overview of the different videos, we so far had an introduction to deep neural networks, then afterward hyperparameter tuning, how to improve these deep neural networks. Then we talked about convolutional neural networks, followed by different popular CNN architectures. And now we finally got to sequence models where we'll be talking about RNN architectures, different gated cells, which can be used for long-term dependencies, a bit about natural language processing, and finally also we'll briefly touch upon transformer networks. But let's start out with a motivation. Let's say we have a single image or some numbers describing where a ball is, and we want to predict its direction. So it could be going in this direction here, or this direction, or this direction here, or this one. But just from this one instance of this ball here, we cannot really say anything more. But giving a single image of a ball cannot say too much, but let's say we also have its previous state and maybe its state two time steps back. So given enough previous placements, it is possible in fact to predict the direction and also the magnitude where this ball is going. So this here is just one example of sequential data. On this slide here, we'll have a lot of different examples of sequential data. So at first, speech recognition, so speaking and turning this into text. It could also be music generation, so it does not need an input, and then it will automatically create some music. It could also be sentiment classification, so for instance, giving a review of a movie, then classify the rating of this user. What is the automatic rating giving this small sentiment? It could also be machine translation, or language translation here, in this case here from Danish to English. Or it could be video activity recognition, so given multiple frames of a video sequence, figure out what is happening in this video. Or another popular thing to use sequence models for is name entity recognition. So in this case here, you want to figure out the names of a sentence. So all of these problems here can be addressed using supervised learning with labeled data, using some form of recurrent neural networks. So before continuing, we'll just be looking at how can we actually embed our words and put them into a deep neural network. And the usual thing to do here is to use a one-hot representation. So words are represented as a one-hot feature representation. So the vocabulary needs to be fixed at some point, with words representing a single entry in a vector. And for commercial applications, a vocabulary of somewhere between 30 and 50,000 words are in fact often used. So let's say we have a sentence like this here. Last week I visited Paris, the capital of France. So for each word we embed into this one-hot representation. And then we can have a look here how some of these representations look like. So for instance, France is the last entry here, which will just have it'll be this vector of somewhere between 30 and 50,000 entries, and then one of these entries will be a 1. So this is one hot representation. So in practice, what you would usually save instead is, instead of this full vector with just one entry being 1 and everything else being 0, what you might save instead is just the entry, which is 1, because you know only one of the entries will be 1. It cannot be multiple entries 1. So in practice, what you would usually do is to save, maybe this here is just the 4th entry, so then you will just save the 4th entry if the word is France. So why can we not use a standard fully connected neural network? So there is quite some problems with a standard fully connected neural network. One of them is that the input and output can be of different length in different examples. For instance, in language translation, it doesn't happen word to word. There's also the problem that such a network does not share features across different locations. For instance, the two sentences, or the first one here, the food was good but not bad at all, which is a positive sentence. The other one, the food was bad, not good at all, is a negative sounding sentence. So you see the placement of good and bad in these cases here essentially mentions if this sentence is, each of these sentences, they are positive or negative. So what we'll be using instead is a recurrent neural network. So giving a neural network, it has some input and an output. This here is just a standard neural network with, in this case, 4 hidden layers. Then to a recurrent neural network, we'll also have an input from the previous state. So A here is the output of all the activation functions. We'll also be putting into the network here. And the output from the first network here, we feed into the next one, and so forth. And this here is what is known as the unrolled representation. What we can also, or how we can also represent this recurrent neural network is in the compact representation. But what is important to know here is that it is not X different neural networks we have here. It's one neural network where you compute the output, then you feed the output A into the network itself, which is also what is visualized in this compact representation with this loop, that the network kind of feeds its output into its own input again. So let's look a bit closer at this RNN notation. So usually, to begin with, the activation here in the initial time step is 0. And then we can compute the activations in the first time step of this neural network by some weight matrix times the activation from the previous time steps, plus some weight matrix times the input, plus some bias term. And the output is then just also another weight matrix times the activation to the output, which also goes out of the network to the next time step, plus some bias term also for the output. So G here, as represented here, is the activation function, and previously, as also mentioned in the other videos, this used to be 10H or sigmoid functions, but nowadays often ReLU is, for instance, used. So the first subscription here of W just defines the output of the multiplication, and the second subscription of W defines what it's being multiplied with. So here the first here A, so it goes into the vector A afterward, also A here, and here we have Y goes into the vector Y and Y. And then we have the second subscript a, it's been multiplied by a, x here is been multiplied by x, a is been multiplied by a, and so on. And here we then have the more general multiplication in the network of both the activation output and the full final output of the network. And one note here is that then this W matrix, it's how it's implemented in practice is often that you just concatenate these two weight matrices into one. So this RNN, it's as such just a standard neural network. The only difference is that it has this additional input from a previous time step, and then it also provides an output for the next time step. So it kind of remembers something about or knows something about where the network was in the previous time step. So the output AFT is just the multiplication between your weights and the input plus some bias term. So we have different types of RNNs. There's the one-to-one, which is the one we have been talking about so far, which is also a CNN network or fully connected networks. They are these one-to-one networks. Then we have a one-to-many, where you just provide one input in the first time step, and then you look at the output in all the others. So one-to-one, the vanilla network. One-to-many, that could be for music generation. Then we have many-to-one, which could be used for sentiment classification. So you provide a full sentence, and you are only interested in the end. For instance, if this movie was good or bad, or how many stars, for instance, 0 to 5 stars. Or it could be many-to-many translation, where it can either be, with 3 inputs, you provide also 3 outputs, or it could be a bit more flexible, just like as in translation, where one language, a sentence in one language might have a different number of words in another language. So far we just saw the very top level, how this deep neural networks are constructed. And we'll just continue that a bit on this side, just looking a bit closer what is actually going on in these neural networks. So in this case here, we have a network with 2 hidden layers, and it's unrolled of 3 time steps. So you could have 3 inputs here and 3 outputs. So this could be the first 3 words of a sentence, for instance, that are being fed in, and also the first 3 outputs. And then we see here that there are 2 hidden layers. So there is some hidden layer here, which could be this simple RNN structure. And it then goes into some nonlinear activation, nonlinear function to our activation function. And then again, we have another hidden state and an activation function more before it goes to some fully connected output here. And there is then a final softmax output. And then we see that from each of these activation functions, this then goes to the input of the hidden state in the next time step. And this here could then continue. So from the third time step here, this would also continue unrolling this network. But as mentioned, all the weights, so in this block here and in this block here, the weights in these 3 here, they are all the same. So this is not 3 different layers, 3 different networks. This is the same network that we're just watching as this unrolled representation. So how do we actually train these networks? Well, let's have a look at here that we have some weight terms and some bias terms, which we are interested in finding the optimal weights for. And now let's look at a forward propagation. So after the activation here of in the first time step, this is propagated to the input of the next time step. And as already mentioned, there is weight sharing here, so all the weights and bias terms in these cells here, the weights are all shared. So in the end, we can then take the output of each of these, compute the loss. If we have X input, and then we also have the ground truth output, so this is labeled data, what it should be. Then we can compute the total cost of all these outputs, how much we're off, and then backpropagate this error through the whole network to update our weights. And this here is also what is known as backpropagation through time. So a quite fancy name, but as such is just the standard backpropagation algorithm that we have been touching on earlier. So what are some problems with standard RNN networks? Well, specifically, long-term feature dependencies are very difficult to learn with a standard RNN. This namely because of the vanishing gradient problem. So just imagine this unrolling the network again and again, maybe have a really long sentence, and now we need to backpropagate this error throughout the whole network. So maybe one of the first words, like the gradient, and comes back to that word from the one of the later words. It's the gradient has then vanished. Let's try to look at two different sentences here. The cat which already ate, or the cats which already ate. And then later on in the sentence, we need to have this long-term dependency, figure out if it was full or were full, if it was single or plural in the sentence here. So the main problem in RNNs is this vanishing/exploding gradient problem. So a possible solution to that is using ReLU activation functions to prevent shrinkage in the gradients. This is also seen in the fully connected neural networks. A second point is initialize the weights to the identity matrix. One should still remember here to initialize the biases to 0. And a third thing is to use a more complex recurrent unit, which gates to control what information is passed through. An example of this is these gated cells are LSTMs or GRU cells, which we'll have a look at now. So in a standard recurrent neural network, we already looked at earlier, it looks like this here. Then we have the updated version, the gated recurrent unit, or the long short-term memory cell here. So GRU, or GRU, is just a newer version of LSTM, which has fewer parameters per cell, which allows for deeper networks with the same number of parameters compared to the LSTM cell. But as such, there is no clear winner between these two, so usually you would try out both to see what works best for a specific application. So as you see, instead of having just this simple activation function in your network, then you would use one of these cells instead, with these kind of gates, they're called, which can then kind of open and close to remember some long-term dependencies. But now let's try to just have a look into the GRU in details and see how it works. So the output can kind of be seen as a memory cell. So remembers, for instance, if a word is singular or plural. And yeah, the output here is just the output of our activation, so our output of our gated cell here. And our gated cell is then a combination of a previous time step, or this C hat. So either it is the C hat, or it is what we have from a previous time step. So either it takes this here or this here. So we just have this G of U, which is the gate U, decides when to update C, so when to update the output. And the intuition between this gamma here is that these gates are always on or off, but in practice they're modeled with a sigmoid function, so the value will be somewhere between 0 and 1, but they're often optimized as that they are, the value will be very, very close to 0, very close to 1. And the star, as shown in the formulation here, is just the element-wise multiplication. Then we also have, let's have an example here. So the cat, which already ate, was full. So once it gets to the cat here, then we are updating the output. And then we keep this gate closed for a long time and then open it again. At least this here is some intuition about when this update gate, as it's called, gate U, gate update, it is 1 or when it's 0. And then there's another gate relevant here, which opens depending on how relevant the last feature is in computing the next output. And the computation of this gated cell here is also shown in the slide here. This is just some intuition about how these gates are updated. Obviously these gates here have a lot of weights to them, which is what we are updating given our whole data set. So we have some, for instance, in language translation, then we feed in one sentence in one language, and the output should then be in another language. And then over time, given our full data set of all of these different sentences that are translated, we'll then figure out when these gates should be open or closed, when they should feed forward, and when the output here should be updated and not. Unfortunately, these gated cells, they are not solving all our problems with long-term dependencies. For instance, in forward propagating a sequence model, it only uses earlier information to predict contextual information. So an example here where we need to figure out if Teddy is a name. He said Teddy Roosevelt was a great president. So in this case here, yes, Teddy seems to be a name. And in the other case, he said teddy bears are on sale. And in that case, Teddy is obviously not a name. So one solution to fix this problem is to use a bidirectional RNN structure, which then takes the input both from the later steps and from the earlier steps at the same time. But this here still has quite some disadvantages, specifically that we're still inputting one word at a time into this network. And then computing one output at a time. So we'll see later on that there is some new methods that are able to overcome this. And even with this bidirectional RNN structure, there is still problems. So let's just have a look at a very specific problem in word context. So some still problematic areas using these, even the bidirectional RNN setup, is words in context. So here we have a small example of translating Danish to English. And just to highlight a few things here, so hence, which is here in the Danish sentence, it's translated to his, but hence is a name. So this should not be translated, but it can also in Danish mean his. So in this case, the translation or machinery here translated the name where it should not have touched the name. Then the second thing is that gid is translated into goat, but in the context of this sentence here, it actually means that something went wrong. So there was no goat in the budget, but something went wrong in the budget. The next thing is rain, which, so he's regner, which can both mean raining, but it can also be calculates or computes. So So he's not raining badly, but he's calculating or computing the numbers of this budget badly. And then there is here /n, which is also something that the machinery here literally was translating to being on the bucket. But this here should instead, or this is a saying used to say if something or someone is in trouble. So he's in trouble at the rest of the month because of this bad computation in his budget. Yeah, as you can see, this tweet here is from 2017. I just tried again here in 2020, and it still seems that at least Google Translate has quite some problems with the sentence here. At least now we see that hence it is now not being translated, or the name still remains a name here. So in natural language processing, or in general just been working with words, then so far we just represented this one hot representation, which is shown here, that we have a vector of 10,000 entries maybe, and then just one of these entries, they are highlighted as one. And one might imagine that, for instance, if you have you want a glass of orange something or apple something, it might be a bit different to generalize from one example of apple juice to another orange juice, or to even more, let's say, exotic kinds of juice, which the translation machinery here might not have seen in its example. So instead of having this one hot representation, what is often done is making some kind of intermediate representation, where the hope is that we learn some kind of features instead. So encoding our one hot representation into some feature representation. And the hope, at least, or the intuition between this feature representation is that we will have similar words located close to each other in this higher dimensional feature space. So for instance, we'll have the word or man and king, so they're both a man, and then they will then have in just some intermediate representation, this gender will have a value close to each other, so -1 and maybe -0.95. And the same with queen, which will then have 1 or 0.97. And then we have apple, orange. They might not have a gender, so they will just have a value of 0. And at the same time, it could be that some people are royal, so a man might not be royal and a woman might not be royal, but both king and queen is some royal titles. So then they might be close in this feature instead. So this here is just the high-level intuition about why one would like some kind of word embedding. One way of embedding a word is using this what is known as word to vec, or word to vector. And this was originally introduced in the paper Distributed Representations of Words and Phrases and Their Compositionality. So the idea here is to train, or the training objective is to learn word vector representations that are good at predicting the nearby words. So for instance, if you have a word cat, then we want to look at, in general, in our whole training data set, how far is the word car from cat in all the different sentences that we're looking at in our training data set. So what we're actually computing here is the conditional probability of car, given that we have cat. So how close is car to cat in a dictionary? And then if we, so how this is optimized is in fact just in the word to vec paper, they're just using a single hidden layer neural network to learn this representation. So we might have an input here of let's say 10,000 words, and then we just have 300 neurons here in the hidden layer. And then this here will just be a matrix multiplication. Let's first look at some intuition about what should be learned in this embedding space. So here we just show some words from an embedding space where we have countries and their capitals, and then by using a PCA prediction, some higher dimension into this 10,000 dimension into just two-dimensional space here, we're trying to visualize the distance between each other. And then we see that there is some distance between all the countries and their capitals. And what we can then do is, for instance, that we can take the point Madrid minus Spain plus France, which should then end up being the closest point is then Paris to where we end up. Just to have some intuition about how this, or what we can use this word embedding for. But as such, as we're only having a single hidden unit in this network, and the input cat here, it's just this one hot representation, 10,000 entries. One entry will be 1, as also shown here. So maybe this here is cat. Then we're multiplying that with our weight matrix, and what we're then taking out is just one single vector from that huge matrix. So as such, this model here just works as a lookup table. As you can also see, this here is from 2013. Nowadays, there are more advanced word embedding techniques. One newer one is, for instance, what is called GLOVE, which stands for Global Vectors for Word Representation. But especially this word embedding is quite important now that we are moving on to the next topic. So we already saw that gated cells, they solve some of the things with the long-term dependencies, but there is definitely still problems with their word context. And another problem with these gated cells is their lack of parallelism. So in modern days, where we have all this graphic card power to power all our neural networks, in fact, in natural language processing, they have for a long time just not been able to run all of these sentence analysis in parallel, but you kind of need to feed in one word at a time, look at the output, and feed in the next word, update the network. So a very long sentence, you then have to feed that through the network feed an input to the network for as long as the sentence is. So a sentence is processed one word at a time, which makes both training and inference very slow. And now we come to transformers, which can process data in parallel. And they're set up in a way, so in a encoder-decoder architecture form, where the system has 6 encoders. So this is just what they were using in the original paper, attention is all you need, and 6 decoders in parallel. And the idea is to learn an attention/importance number for each word in a sentence. So here is the transformer model architecture, which we'll just briefly be touching upon. So a sample sentence could be the cat is brown, which would then have some attention here. So what we're looking at here is the average attention vector over n parallel systems. So here we have n, which in the original paper was set to 6 encoders. So we'll have our input, the cat is brown. This is put in here all in parallel. And then we're doing the word embedding. Each word is embedded. We are also adding a positional encoder to this embedding, such that we know where in the sentence this word is positioned. And then we have this full multi-head attention, which is being run n times, which will then produce such an attention matrix here. Then it goes through into a another fully connected neural network. And it have to be said that all of these 6 encoders here, they do not share weights. Then afterward, it goes over into the decoder, where again there's an attention layer. It goes through, and then a fully connected layer before it goes to the output. So for instance, the translation of this sentence here, the cat is brown. So to begin with, there'll be an SOS down here as the input, which is the start of sentence. Then we feed in the sentence. The output, the first output of this decoder network would then be katten, if we're translating to Danish. Then this word here gets removed from here, goes down to the input. So there's still some recurrent stuff happening here, at least in the decoder. Then we're feeding the first word into the to the network, which is why we have this masked, or which is what this covers over, masked multi-head attention. So obviously in this case here, masked multi-head attention, we cannot compute a full matrix here. So to begin with, we only have the start of word, and then now we have katten, and then essentially all these other entries, if we just have one word to begin with, they will then be empty. Like we do not have all of those entries. We do not know what later comes in this sentence. Okay, so then we put in katten. Then we'll figure out that the next output is and then brun. So the final sentence was katten er brun, and then it'll be followed by a end of sentence, which will then be output. So the network always, in this case of translation at least, then it has the start of sentence to begin with, and then whenever the sentence is done, we'll just send an end of sentence to the output, and then we have the full translation of a sentence. So as you can see here, this here was just the very, like the essential of the structure of these transformer networks. We can have, I guess, a full lecture just on how these transformers are working, and really going into details with every single step here, both the encoder and the decoder, and the coding, how everything is structured. But the slide here is really just to try to give you a high level intuition about what transformers are, what they're doing, and where you might be able to use them. So with that, we come to the end of sequence modeling, and therefore we have a small summary here. So RNNs, they can be used to model sequential tasks. And model sequences are traditionally modeled via a recurrence relation. Training these recurrent neural networks can be done with backpropagation through time and a gradient-based optimizer. Then we have these gated cells like GRU, let us model reasonable long-term dependencies. But RNNs, they suffer from slow training and inference time. And slow inference time. So to the rescue comes these transformer networks, which works in parallel and can model very long-term dependencies.